Welcome to our discussion on how to analyze arguments using truth tables. Here are the topics we're going to hit. Truth tables with two premises. We'll talk about valid and invalid argument forms. Then we'll look at truth tables with more than two premises. And if we have time, we'll look at some arguments of Lewis Carroll. Okay, so in previous lessons, we've seen how Euler diagrams can be used very efficiently to test the validity of arguments. But those Euler diagrams really only work well with very simple arguments. If the arguments have those universal quantifiers like all or no or some, then it works well. But if those things aren't there, then it gets kind of messy, and oftentimes it's better to use a truth table to try and figure out validity of those types of arguments. So how do we test the validity of an argument with a truth table? Well, the first thing we need to do is assign a letter to each piece of the argument. Then we need to express each premise and the conclusion symbolically using, conjunctions, disjunctions, conditionals, i.e. the ors, the ands, and the little arrows. After we've done that, we need to form the symbolic statement of the entire argument, so all the pieces put together, by writing the conjunction of all the premises, i.e. all the first bits and pieces before the conclusion are all put together in a conjunction. Remember, conjunction means with a bunch of ands. And then the antecedent of the conditional statement, that's going to be that's the first part of the if-then. So you get a big old conjunction, that's the if part, and then the conclusion just becomes the then. This will make more sense once we see an example. So basically, you're going to take all of the bits and pieces of the argument, and then there's a conclusion of the argument, right? So all those bits and pieces get put together in one big string with a bunch of ands, and they become the if part. Then you have the arrow going to the then part, and the then part is the conclusion. So you're basically saying, if all of these things with ands in between them are true, then this last thing should also be true, because that's your argument, right? Now, we can complete, once we have all that, we make a big old truth table, and we complete the truth table. And if the truth table is a tautology, and if you remember what that means, it just means everything has to be true in the end, right? Intermediate steps, not so much. But when you evaluate the entire if-then statement as a whole, if you get nothing but trues, right, TTTs all the way down, then it's called a tautology. And if that's true, then your argument is valid. If there's a false anywhere in there, it's invalid. Okay, let's look at our first example. So is the following argument valid? Well, we got, if the door is open, then I must close it. The door is open, and then the line, conclusion, I must close it. So can you see how the first two lines are all the bits and pieces that we're going to put with and pieces, right, with conjunctions, and then we're going to have, if all of this, then the bottom. So let's first give everything some letters. So we'll let P represent the door is open, Q represent I must close it. So if the door is open, then I must close it. That's if P, then Q. Here, the door is open. That's just saying P. And then I must close it. That's Q. So here's the same argument, just in symbols. Now, the rule is we take these top two pieces, put them together with an and then make that the first part of an if-then to the conclusion. And here's what that looks like, right? So here's the first premise. That was the P implies Q, right? If the door is open, then I must close it. And the door is open. Those were the two parts of the premise. So premise and premise, right? So if the door is open, then I must close it. And the door is open. And so if all of this is true, then implies the conclusion, I must close it. So now in order to figure out if this is a tautology or not, we have to do a truth table. And oftentimes your book will just like show you the final result. It'll just say, oh, here's T's and F's for the final thing. I can never do this many steps in my head. So I do it in pieces. So let's take the first piece. P implies Q. So we treat it like a normal if-then statement. And remember, it's true for every possibility except for when the first thing is true and the second thing is false, right? So if this happened and this didn't happen, then that means if then is false, but it's true everywhere else. Okay, and then now we're going to do the AND argument. So if we put these two pieces together, remember an AND argument is true only when both pieces are true. So this is true and P is true, right? False, well, that ruins it. And then P is false for both of those, so that ruins it. And it's only true in one place. Okay, now we can do the final piece, which is basically looking at this whole thing implying Q. Well, the whole thing, I used this symbol, right? This is basically representing that whole argument. I put those two pieces together. And so now we're basically saying what happens when we look at these things implying Q. So true implies true. False implies false. Well, that's true. False implies true. Well, that's also true. And false implies false. That's true. Right? Because remember, the only time a conditional fails is when the first thing is true. Well, this is the only time the first thing is true, and the second thing is false. But Q was true. So true went to true, and then when the first thing is false, the whole thing is just it's called trivially true, right? It's true because you can't even evaluate the argument. All right, and so if you went to the book, they would just go straight to this and go, hey, look, they're all true, without showing you the steps. I think it's better to see the steps, then you can see kind of how you got there. But because they're all true, then it's a tautology, and this argument is valid. If the door is open, then I must close it. The door is open, so therefore I must close it. Here are some valid argument forms. If you want to memorize these, then whenever you come across something in this form, you know it's a valid argument. We just saw an example of this one. If you come across something with any of these other symbol organizations, then you know it will be a tautology and you know it will be true. So if you want to put that in your notes, that's fine. But rather than trying to memorize things, I say just do a truth table each time and figure it out that way. Here are some invalid argument forms, or what we call fallacies. So anytime you see arguments that are made up in this way, you know that it's going to be false. Again, if you want to memorize them or have in your notes, that's great, but just do the tables. Okay, here's another example. Determine whether the argument is valid or invalid. And this is a long one. If Pat goes skiing, then Amy stays home. If Amy does not stay at home, then Cade will play video games. Cade will not play video games. Therefore, Pat does not go skiing. So now we have to put in letters for all the bits and pieces. So we're going to let P be the first statement, Pat goes skiing. Q be the second one, Amy stays at home. And then R be the third one, Cade will play video games. And you'll notice that it's not so much that it's because it was the first way it was written. You know, the first time it talked about Amy, it was Amy stays at home, and then Amy does not stay at home. We don't let Q represent Amy stays at home because it was first, because you know these are both statements about Amy and being at home. Either one of them could be Q, and then the other one is obviously the inverse of Q. It's just easier to wrap our brains around it if Q represents a positive statement, right? Amy does stay at home. And then this is going to be the inverse of Q, not Q, right? We're going to call this the inverse of Q because this Amy does not stay at home. And it just makes sense. Our brains kind of see this symbol and think of a negative sign, and they think of it as a negative Q, and does not is the negative sense. So it makes it a lot easier for to wrap your brain around how this works if you always let your P's, Q's, R's, all your letters represent the positive version of all the statements and then negate them accordingly if you need to. So if we translate everything it said, right? So the first statement was, if Pat goes skiing, then Amy stays home. So if P, then Q. And the second statement says, if Amy does not stay at home, so there's the not Q, then Cade will play video games. There's the R. Then the next statement just said, Cade will not play video games, right? It's just a statement. It wasn't a conditional. So Cade will not play video games. And then the conclusion was, therefore, right, here's our therefore line, Pat does not go skiing, the inverse of P. And if we want to figure out a truth table, remember we have to take all three of these and put them together with ands, right? So the first piece and the second piece and the third piece. We're basically saying if all three of these pieces happen, then not P is supposed to happen. And again, we're going to evaluate this with truth tables. The book just gives you an answer, right, at the end and says, oh no, it's invalid because you got this F. But you're never going to figure out how they got there in one step. So we'll do it in stages. So here's not P, not Q, and not R. So false, false, false. And then by the magic of video editing, here is all of those put together. It's a typical pattern of how to do a three-way truth table with your truths and falses, right? You get 4 and 4, and then 2, 2, and 2, and then 1, 1, 1, 1, 1. It's just how it works. Okay, now that we have all of those, we can finish up the rest of these, right? Because you can see that the negative pieces are over here. But again, we're just going to take it in pieces. First, I'm going to figure out what P implies Q is. And we'll do that in blue so we know that's what these represent. So P implies Q. Remember, P implies Q is always true except for true implies false and true implies false. So true, true, false, false, true, 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 true. Okay. Now let's do the second piece, the not Q implies R piece, which means we have to use not Q. So all this stuff, right, the not Q, and then implies R, so we're looking at R. We'll do that one in green. Again, remember, implications are only, right, conditionals are only false when the first part is true and the second part is false. So that will only happen when the first part is true, and then from those, okay, this one's false, and this one's false, right? Those are the only time when the whole thing is false. Every time else, we're good to go. So false and false. The rest are all true. Now, we can do their and. And remember that ands are only true when they're both true. And they're false whenever one or both of them are false. So now these two pieces have now been put together, and they're represented by the red stuff. And we can pretty much ignore the green and the blue. Like if we wanted to, we could erase them. All right, now the last piece we have to do, and we'll do this, I guess, in black, is we're going to look at putting them together, right, with not R. We're going to look at these two pieces and this piece. And again, it's only true when both things are true. So we know right off the bat, it's got to be false here, here, and here, because that's when, right, the first part is false. And then now we have to look at what happens with not R, and we can see it's false here, it's true here, right? It's false here, true there, and false there. All right, so now this final column represents all three pieces put together. So it's basically everything inside the square brackets is right here. So we can see that it's mostly false, which makes sense. If we have three pieces, this and this and this, and the only way it's true is when all three pieces are true, there's going to be, a lot more falses than trues. Okay, now we have that we're looking at one whole big thing is like one big P. So we now have like one big huge P, implying this not P, but it's not the same P, right? So I don't know, maybe we'll call it B. And these all represent B, right? That's our B column. And we know that a conditional is only false if the first part is true and the second part is false. So if the first part is false, they're always true. So that's why we can see we have true, 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 right? True, true for all those falses. And then all we have to do is check the two trues. So true going to not P, true going to false, there's a false. And then this one, true going to true, there's a true. And this is the only one that messes us up. So it was almost a tautology, but there was one place where it just wasn't true. So because of that, it's not a tautology, and therefore our argument is invalid. Okay, our last example is how can we use this idea to kind of create a statement that makes the argument valid. And these are called arguments of Lewis Carroll because they're all these statements that come from Lewis Carroll books, like like Alice in Wonderland and various other things. All right, so here are some statements. Babies are illogical. Nobody is despised who can manage a crocodile, and then illogical persons are despised. So we can let P be you are a baby, Q be you are illogical. Sorry, you are logical. Remember, we always want to make these things be the positive, so illogical will be the negative. R will be you can manage a crocodile, and then S will be you are despised. So you see we've picked out all four of kind of the adjectives: being a baby, being logical, being able to manage a crocodile, and being despised. And all four of those get letters. Now, let's rewrite what we have with these symbols. So the first one, babies are illogical. Well, remember, P was you are a baby. Q was you are logical. So babies are illogical means if you are a baby, then you are illogical. So if P, then not Q. The second one said, nobody is despised who can manage a crocodile. Well, you can manage a crocodile was R, and nobody is despised who can manage a crocodile basically says if you can manage a crocodile, then you aren't despised, right? So R goes to not S because S was you are despised. So not being despised is not S. And then the last statement, an illogical persons are despised, meaning if you are illogical, then you are despised. Well, then that means, remember, Q was logical, so illogical is Q, and then despised was S. So those are our three statements. Now, beginning with P, and then using the contrapositive, we can form the following things. P implies not Q. We have right here that not Q implies S. And then from the contrapositive, because remember a statement and its contrapositive are equivalent. So R implies not S is equivalent to switch the direction and switch their things. So it goes in this direction and it becomes S implies not R. So these three statements are equivalent to these three statements. We have the first and the third, and then second one we just use a contrapositive, and then we just reorder them, but it's still the same three things. But by doing that, you see how we have created a transitive theory, right? P goes to not Q goes to S, S goes to not R, so by kind of a double transitive, we have that P implies not R. So there is our final, that would be a valid argument by the reasoning by transitivity. It was one of the rules that we saw earlier. So if we have the statement P implies not R as kind of our conclusion, then we have a valid argument. And if we put that back into the words, P was you are a baby, R was you can manage a crocodile, so this would be if you are a baby, then you cannot manage a crocodile. I know it's totally stupid, but that's the Lewis Carroll stuff, okay?